So the purpose of this talk is to refresh our last talk and then go into Ginzburg-Landau formalism. So essentially, we are still dealing with BCS theory of superconductivity. That was quite a breakthrough theory. Actually, Feynman couldn't solve the puzzle of superconductivity. It was solved by Barden, Cooper, Schreifer. I would say Cooper has created Cooper pair concept, and then the whole theory was constructed by three guys. So yeah, let me shortly refresh the whole scheme of hierarchy of theories and phenomena in superconductivity. So essentially, we have the Nobel Prize winners on the right side of the slide. So, and we are still dealing with the theory which directly comes from BCS theory of superconductivity, and this is about Broglie-Dijen equations. This is a mean field theory, and this mean field theory, well, it has certain shortcomings, but still it has also, I would say, it's quite powerful in description. If you want to go deeper, you can go into Eliashberg theory of superconductivity, which gives you more detailed view of pairing mechanisms. Yeah, we will focus later on Josephson junction physics, and also later on levitation phenomena. And then, so at first we'll finish the description from last week about BCS theory and about Broglie-Dijen equations, and then we'll move towards simplified theory of superconductivity near critical temperature, which is a Ginzburg-Landau theory. Actually, historically, Ginzburg-Landau theory was in 1950 and BCS was in 1957, as you can see. And all nanostructures, mesoscopic structures, could be tackled with this both theories. And of course, it's somehow understandable that more phenomenological theory is the less parameter it has, and in the simple structure it has, usually it's going to describe the reality in less exact way. All right, so yeah, so this is standard tunneling Josephson junction Hamiltonian, and then I want to underline that you can describe this. So you are always getting measurements and results of your experiment, and then you can parameterize obtained data by this phenomenological Hamiltonian, which is two, which is actually two fluid model. So you pre-assume two quantum systems. So left and right superconductor are weakly interacting. So this interaction doesn't differ too much less than superconductor on the left side and right side. So this is two fluid model. RCSG model is two fluid model. Then you can describe this structure by Bogoliubov-Dijen equations, essentially by BCS theory, which is a subject of today's lecture. And also you can describe the same structure by Ginzburg-Landau theory. So to say it, it's like three different formalisms of different complexity describing you this structure. And we have already know that we can end up having two fluid model. We can end up in our RCSJ model, which is very good for highly integrated Josephson junction circuits. Is nothing else as nonlinear pendulum problem. This is nothing else as nonlinear pendulum problem. And then there was a washboard potential concept which was derived on last lectures, and then we have quantized this pendulum, nonlinear pendulum. We have quantized it. So the quantization procedure was attempted with with pre-assumption that generalized position and generalized momentum does not commute as it is in standard quantum mechanics. And then we have obtained a kind of Schrödinger equation for Josephson junction basing on this two-fluid model. We do remember that we have omitted resistance. We have, in this quantization procedure, we have omitted resistance, but actually we can recome back. Then if we recome back, then we would get non-Hermitian Hamiltonian, which will account for some level of dissipation. You can treat it as homework. I'm just trying you to give just general insight. I mean, that's also a question: what is a lecturer role? And lecturer role is quite often associated with being a guidance, with being a guide among different types of books. This is old style. So it's like in modern style, more and more often the lecturer is treated as a kind of audiobook at some point. So that just reads you some kind of note or instructions. But in old style, it's about essence of philosophy. And then the audience or students, they're dealing with, they digest this philosophy or they apply this philosophy in more detailed cases. All right, so this is how things are done with so far. So we are right now trying to touch 3 different formalisms for description of the same phenomena. And basically we're supposed to get convergent results. It's just for your recognition. So if the current flow across the structure is proportional to phase difference between a left and right wave function, then it does mean that it's supposed to be the same in Ginzburg-Randolph formalism, the same in Bogoliubov-Dijon formalism, and the same in two-fluid model. And of course, the easiest is to obtain this AC and DC Josephson effect in this two-fluid model, and we already did it a couple of times. All right. So this is this hierarchy of the theories, so basically we have touched two-fluid models so far. We have, in a sense, a little bit touched Bogoliubov-Dijon equations, and we are likely to touch Ginzburg-Randolph equations. So we are at this bottom. But if you want to be at the top, we can go into Hubbard model or Eliashberg's theory and Gorkov propagator. It's a subject of 2 or 3 semester lecture in a sense, but it's worth of dealing with because, well, it's as I suppose you're supposed to know how important are Josephson junctions, for example, and in quantum information processing. So it's not a big surprise for you that in order to pursue very ambitious goals, like you need to put a lot of focus and attention on mastering certain type of skills. Like you can study the IBM quantum experience documentation and see how deeply you can go. By the way, we have new quantum computer in Poland. This is Wrocław. This is this IQM computer, which is based on superconducting Josephson junctions. So if you want to contribute to new type of chips, you need to study theory, to develop nanostructures, you need to characterize nanostructures, you need to combine both theory and experiment in order to contribute to new types of chips. It's up to you, of course. All right, so let me continue. And this is just example of this constriction. So any structure with some narrowing of that diminished superconductivity order per meter can be basically treated as a type of Josephson junction. Of course, the easiest way is to separate 2 superconductors by non-superconducting insulating material, but still you can have, let's say, different types of architectures like superconductor normal metal superconductor, and so on. So you can also, there is a lot of nice experiments with superconductor molecule superconductor. So you can study the spectrum of molecule by creating very special type of Josephson junction. That's also quite nice. And this is the case of ferromagnetic strip on the top, which is one type of Josephson junction that is tunable. All right, so it has two regimes of behavior, like tunneling Josephson junction or just weak link type. Here the dominant feature is rather a weak link type. And then there is this phenomena which needs to be fitted also by Bogioff-Dijen theory, especially, is this unrebound states. So there is a very nice phenomena that preserves CPT symmetry. So charge conjugation, parity, and reverse and time inverse stands for CPT, at the same time stands for CPT symmetry. So basically, Hall can be treated as antiparticle to electron. Hall is a lack of electron. So if you have atomic cores, if you kick out of the electron from atomic core to atomic interspace, then you have some Hall that, and this Hall is likely to be compensated by neighboring atomic cores that they're likely to emit electron to the place where there is a Hall. So the Hall propagates, and the Hall has the same propagation property as electron, basically. Well, it can have slightly different effective mass, and so the Hall has associated property as particle. If you try to think from classical physics perspective, there is a very excellent example you can find out. You have bubble in the water. You have submarines sometimes emit some air bubbles, and this bubble is going against gravity. So actually, you can associate it like negative mass or something like that, right? So and just think how to parameterize even via Newton equations of motion the bubble in the water. Can you associate the mass? And think how to do it. It's just so this is a little bit the concept of Hall, moving Hall. All right, so there is electron incoming to the superconductor, and in the superconductor the dominant transport is by Cooper pairs. So in two fluid models you have paired electrons, which stands for Cooper pair, and it's like boson liquid, boson quasi-boson liquid that is subjected to Bose-Einstein condensation, and then there is a unpaired liquid of holes and electrons that are unpaired, so they don't create a bound state. And the bosons are subjected to Bose statistics, which allows them for a very high density. So there is, in Bose-Einstein condensates, there is no limit on possible density of matter. That's why in Bose-Einstein condensate, the light can propagate sometimes a few centimeters per second. There were some people that has created such chip that controls Bose-Einstein density, and then you can control the speed of light in the medium. Yeah, so this is Bose-Einstein condensate. And then at the same time, there's occurrence of Fermi liquid, which is subjected to Fermi Dirac distributions, and then there's natural limitations on the density as fermions cannot be, squeezed too much. And then there's white dwarfs that cannot have certain density of matter above certain value. For example, the end of stars, white dwarfs. Yeah. So basically, the resistance is due to occurrence of Fermi liquid or unpaired electrons as they generate the ohmic law. So there's coexistence. But here on this picture, there's only assumption that dominant mode of transport in superconductor is by Cooper pairs. So it's very good to make a kind of self-considerations at home with this, how to compute this bound state. Andrew bound state, which accounts for a Josephson effect. So basically, Josephson junction properties are expressed by properties of Andrew bound state, and then it's so this Andrew reflection is accounted by Bogoliov-Digenich formalism, but it's not accounted well by Ginzburg-Landau formalism. It's information for you. And detailed descriptions of superconducting qubit cannot be fully achieved by Ginzburg-Landau, because Ginzburg-Landau equations doesn't give you exact spectrum of quasi-particles. It's just some information for you. Well, this washboard potential can give you some hint to quantization, but it's less exact than Bogoliov-Digenich. All right. And also, for the sake of physics universality, one also supposed to compare the Bogoliov-Digenich equations with Dirac equations. They have a little bit, not the same, but bit similar structure. So there is particle and antiparticle. And then there is certain nonlinear feature which is encoded in Bogoliov-Digenich equations, and this is self-consistent relation, and this will be very much troublesome, simply because how to say, you'll see, apart from very few cases, you will be forced to solve Bogoliov-Digenich equations in a numerical way. All right, I will give you a hint how to tackle this problem, but we'll do step by step. All right. Okay, this is this famous triangle, and this famous triangle probably is the best dealt with, well, I would say Bogoliov-Digenich equations at some point. I mean, Josephson effect and single electron transistor. There's a Cooper pair box concept, which also needs its own lecture. Yeah, it can both be described by certain version of Bogoliov-Digenich Hamiltonian. There are some edge currents which occur in superconductor, and there are also edge currents which compute in quantum Hall effect. It's a subject of your future interest. And well, let me postpone this quantum Hall effect type of currents for later. All right, do you already know this concept of two Bose-Einstein condensates coupling, and there are certain IV characteristics which you are able to derive, for example, from RCSJ model. It's just a matter of your exercise. In one case, in a weak link, you can pre-assume there is no capacitance. So it's essentially first order differential equation. And in case of weak link, you cannot forget about this presence of capacitance. So it's second order differential equations, and you're supposed to get these IV characteristics. What is prominent for this both characteristics is there is a peak current, peak flow of current without voltage drop. That's a remarkable feature of superconductors, which accounts for the non-dissipative phenomena as presence of electric current due to movement of paired electrons, or essentially due to movement of Cooper pairs, like bosonic liquid. All right, and this is what we have already started talk last time. So essentially we have, so the first question was how to construct a Cooper pair which is bound state of two electrons. And I would say that let us consider a kind of general approach to two interacting particles. So essentially, the essence of Schrödinger, what Schrödinger equation does, it encodes mechanical energy, that is a sum of kinetic and potential energy, preservation of mechanical energy. So it is trivial and non-trivial, depends how you view this, but essentially it does says that you have kinetic energy operator for each acting for each particle, then you have effective potential for each particle, and then there is mutual interaction of two particles. So this is like two-body problem. And usually it's reasonable to assume that two-body interaction, the two-body potential is about this, is parameterized in a unique way by distance, right? Between two, it's reasonable to have it. So in that sense, you have, for example, the Coulomb potential, right? But in principle, you're supposed also to get this Yukawa potential, for example, also can have similar feature. Yukawa potential is different from Schrödinger potential by decaying factor, exponential decaying factor. And actually, yeah, so it's just two-body problem, and it's good to have some experience having two-body problems in quantum mechanics, because like two interacting qubits is also two-body problem essentially, or n-body interacting qubits is n-body problem. Of course, the problems accommodate with number of particles quite rapidly. You cannot effectively go beyond 10 interacting particles in a rigorous way. But anyway, let us start with two interacting particles. So it's for certain, it's a convenient to move to momentum representation. So the same equation one can be described by momentum representation. And then it's nothing else as so you move from position, you have wave function position representation, then you take Fourier transform over it. And then so it's minus h bar over 2n d square over dx1 square is momentum operator in position representation. And when you have momentum square operator in wave vector in moment, when you move to momentum representation, there is multiplication by k1 square instead of derivative. On the other hand, you have to take Fourier transform of potentials, and it's you have to check it by yourself, but there's the Coulomb potential is troublesome with having the Fourier transform, since it doesn't really exist. So you have to assume the Yukawa potential with certain limit. So then you have unique the Fourier transform of Yukawa potential that can also mimic Coulomb potential. But essentially what is important is that two particles interact by exchange of momentum. Exchange of momentum, this is especially well seen in momentum representation. So so for example, Coulomb potential could be you can associate existence of virtual particles as photons that are emitted and absorbed. But it's the prescription, you have K1 minus K2. It's essentially important to see that one particle is kicking another particle, in simple words. All right, I'll let you move on. And then there is this what I have already mentioned, the two particle interacting potential in momentum representation, right? And then in case of Cooper pairs, well, if you go to original Cooper paper from 1957, it's written in very short words, I would say. So there was a suspicion that there is this, because if you have superconductor, you have certain unique phenomena. You have very high current density. You can have kiloamperes per centimeter square, and the material does not heat up. Of course, if you have a material like in room temperature, it will heat up, but it doesn't heat up at low temperatures. It's very unique. So these unusual current densities, for example, are not typical for Fermi liquids. They are typical for Bose-Einstein liquid. So they have created this Cooper pair that concept that there is interaction of two electrons at the distance of 1,000 angstrom, which is like 1,000 to 3,000 angstrom, which is from like 100 to 300 nanometers, which is mediated by phonons, not photons, phonons. So the vibrations of crystal lattice, quantized vibrations of crystal lattice. So this is like Fröhlich Hamiltonian if you want to go into detail, but essentially the simplified situation in case of metals, if you have atomic cores that are positively charged and there is a moving electron in between, so like on one line, on another line, and since moving electron is attracting cores, so from high distance, two electrons will attract, but when they come too close, they repel due to Coulomb propulsion of two of the same charges of the same value and sign charge. Okay, and then what is written in essentially in original Cooper paper and then BCS original paper, the Nobel winner paper, please go to download it, try to digest the original source of knowledge. Then it's only written that this VK1, K2 is minus V, as the formula 4 points out. So there is pre-assumption that in metal, like SPB or niobium, for example, or NBN, niobium nitride, then the formula is minus, it's essentially minus V. This is very much phenomenological assumption. But this is only, so K1 and K2 are in very narrow limit of values. You are very close to Fermi energy. Well, the Fermi energy is energy when I would say, in the case of, for example, metal, when all atomic cores are filled and there is every electron is associated with, so all cores are filled. Whenever you deliver the energy to atom, some electrons from high orbits are easily excited since they have low bound energy, they're not so much bounded with atoms, so they move into interspace distance between atoms. So the BCS pairing is of very small value, as you can find out. BCS gap is in case of media electron volts. So so there is KF, as you see this, there's small change of K, and then the pairing is zero otherwise. And then you can write two-body wave function postulating by such operator as here. So it's essentially, it's nothing else as postulate about plane waves. So you have, okay, I will maybe put it here. So you need to see that you have this energy of center of mass for two electrons, and there is a big capital K letter, which this is energy of center of mass of 2 electrons, and there's energy in reference to center of mass with not capital K letter. And then you can summarize the Schrödinger equation by this guy which is written here, but this is in momentum. This is in momentum representation, right? And so kinetic energy. So you have kinetic energy of center of mass plus 2 electrons, or 2 electrons energy, kinetic energy in reference to center of mass. This is E is total energy, and then there is a pairing part. Okay, so let me move on. All right, so we are just consequent in dealing with previous equations. So so what we have is this equation. This is what was written on the previous page, and then due to the fact of being constant, well, you can replace this sum with this sum as in that way, and then you are having this form as specified here. So this is troublesome kind of formulation, because this formulation actually, I would say, the K is dependent on another case, right? This you need to solve this AK problem. Well, you can use tricks with normalization, uniformity of certain solutions and normalization, and then by having the sum on both sides, you can transform this equation to that equation. That is later going to be transformed to that equation. And this is will be almost superconducting gap equation obtained in very phenomenological way. Well, here we assume that the whole mechanical energy of the system is kinetic energy of center of mass for 2 electrons, their kinetic energy in reference to center of mass, and there is a minus condensate energy, superconducting condensate energy. So it's like bound state energy that's supposed to have negative. It's like if you have the Earth rotating around Sun, then if you compute the mechanical energy of 2 bodies, since they are bounded, the total mechanical energy needs to be negative. So that there is this is very important because there is minus delta sign, and delta is a real value or complex value scalar field. Here it will be complex, the real, let's say for the sake of simplicity, real value. All right, so so this is this gap equation, which is equation for superconducting gap, delta delta, and this is what you see, what can be written in that way. The state's density at Fermi level, and this is written in that way. It's up to you to. I'm just giving you this kind of conceptual projection. I mean, just believe me that the superconductivity phenomena, you have to go via different courses on solid state physics and condensed matter to tackle things in a very deep way. Well, there are a lot of famous books like Fetter-Walecka book, or this book on also very known. This because of Gorkov and Dzierżynski are all Russia physicists. Methods of quantum field theory in statistical physics, but there's a lot of layers of complexity to be tackled. Anyway, I would try to be as simple as possible if I can. All right, so let me move on. All right, and then there is this BCS theory, which is of that structure as given here. Now it's before a BCS theory. This is still before. So you have to deal with second quantization. So second quantization is the modification of first quantization, basically from the fact that you are associating the creation and annihilation operators to a wave function. This is essentially what it is. So if you do description of, let's say, description of quantum system in first, with just Schrodinger equation is first quantization, you presume existence of the particle all the time. In second quantization, there is a probability that given particle exists, and there is also another probability that the more or less number of particles are existing. So you are subjecting the existence of particle to a probability. So this is another layer of probability. So this is the modification of second quantization is modification of first quantization in that sense. So here it's with existence of creation and annihilation operators, very much referring to the potential, harmonic potential philosophy. You need to understand that. Yeah, so then there is a pairing two-body interaction that is also dependent on the spin, as you can see here. And this is the form of two-body interaction before any mean field simplifications. So it's quite hard to be solved, but it can be attempted. You can try to find certain numerical solutions without this. It's just open problem for you to consider for future. But when you are dealing with this BCS pairing in momentum, as it was pointed out before, you are essentially getting the sum such simplification as given here, and then also to go further with levels of simplification, you assume that the correlations between fluctuations is zero. So there is A operator and its mean value. So A minus its mean value, that B minus its mean value is zero. So this formula constitutes mean field assumption, essentially. All mean field theories can be somehow approximated by it. It's not always the case because simply there are some examples where mean field theory assumption doesn't work. For example, you can have Hartree-Fock mean field theory assumption that you can have movement of electron in n-body system, and you can presume that n-1 bodies are creating effective field that is affecting given electron. But not always this replacement of effective field, of replacement of many electrons by effective fields is valid. It's not always it's valid. There are some cases known where it's not. Anyway, we have this mean field assumption, and then we need to build operators B, which is either, it could be Daga here, but it can be also in that way. So essentially, two creators or two annihilation operators are assumed to have mean value, which we later refer to this superconductivity or the parameter. And with this assumption, we are simplifying this 7 by assumptions from 8. All right, so we already have two assumptions here, right? And then what we are going to get. So original Hamiltonian is going to be described pretty much as by formula 9. And here you have coexistence of two annihilation operators and two creation operators. So there is certain level of simplifications because here we have coexistence of both two creations and two annihilations operators. There is a price you need to pay for it by assumption of existence of this expression and this expression, but still, or this expression, but this is so-called self-consistency relation. So you presume there exists complex value delta K prime field, which can be obtained by such a sum, and also parameterized in such a way as given here. Yeah, so in reference to that, it's supposed to be dagger here, right? So you have equation 10. All right, so, and then, yeah, so let us be more direct and more insightful. Let us plug in this this new field, postulated field. So there's this. Also, it's the consequence of this mean field assumption approximations that AB operators can be always written as in that form. It's just this. I'm just by the chain of simple operations, I obtain this AB formula as given here, right? Is everything correct here? I'm just checking minus here. I'm sorry. Okay, anyway. So we are getting this this expression as given here. Basically, it leads us to such assumption as given here. So we have the simplified Hamiltonian. So there's kinetic energy. The condensation energy is a minus. But there are still the coexistence of two creation and two annihilation operators. And basically, it's a matter of linguistics or just some reference to existing examples, but we used to say that theory that can describe the creation and annihilation operators like very easily. So this is operator for nothing else as number of particles. It's a diagonal form of theory. So we want to diagonalize. So we want to change a basis. So we want to introduce such operators that our theory will be described by creation and annihilation operators only. So we need to change basis. Yeah, so we have this equation 13, and then, yeah, so we need to do this transformation. And this is the story. So we have creation. So just to make summary. So with this A K spin up is annihilation operator. It's fermionic annihilation operator. And this fermionic annihilation operator has to have such commutation rules or anti-commutation rules that that will not allow for coexistence of two particles at the same position in space, right? So then I'm just trying to push you towards this. So you have to understand what is this. So in case of two bosons are essentially, they can be replaced. There is no change of wave function if you exchange two particles, bosonic particles. If you exchange two positions of the electrons and their spin, there must be minus sign. So it gives you a hint about computational rules. Anyway, this so they basically need to anti-commute. Anyway, so this is the operator to creation operators. We introduce new type of operators, alpha and beta, and there is a linear combination of them. So this you can see as this is, and this is we had a certain normalization condition. So we introduced. So we want to transform the previous form, but this transform, or of course, equivalent way of writing is by equation 16. By equation 16, right? So and so this can be done both back and forth, this operation. And of course, if you want to transform these equations, you have for 15. There are new functions that come into it. It's UK and VK. And these functions will be later seen as wave function of electron in a hole, actually. But so far we have just numbers. And then the UK and VK are chosen in such a way that final structure of Hamiltonian is as equation 17. So it has only creation and annihilation operators in that way. So there's no two annihilation operators, alpha and or two creation two. So there is this problem which is, so in that sense it's a bit similar to canonical example of harmonic oscillator in that sense in quantum mechanics, right? So there's of course condensation energy and so on, right? And then you can write this equation, this Hamiltonian, in such a way as given here. There is Daga here. So it is in that form, and this is just a scalar, complex value scalar. This is nothing interesting. Well, if you introduce this transformation as before, you can also write it in alpha, in Bogoliubon's base, in a sense. The essential thing is that you're having this eigenvalue problem. Is this kinetic energy minus kinetic energy, and this anti-diagonal, you have this condensation energy. So this is a little bit like Dirac equation structure. So this Hamiltonian acting on the state is giving eigenvalue times the state. And then you are having this type of equations. So this is as from classical, how to say, classical mechanics, not classical mechanics, from classical quantum mechanics, let's say. You know, this H0, this is just the story with the particle in effective potential. This is H0. So you are having this, and U and Vn are wave functions of electron and hole, and then just remember this guy. This is in position representation. This also will be transferred to. This is momentum presentation, will be transferred to position presentation, and you see this is on. There's supposed to be Daga here. I'm sorry. So on the anti-diagonal, in anti-diagonal place in matrix, you have this superconducting order parameter, and then the Hamiltonian, you need to find the eigenstates of such Hamiltonian. So it's first observations which, well, this might be, this equation, even that structure in that form might be fully true if there is no magnetic field. There would be Daga will have the same form as so in case of no vector potential, this is the form as it is written. So electrons and holes are not correlated. They are not correlated if there's no superconductivity. So above TC, above critical temperature of superconductor, where it transfers to be non-superconductor, there is no this simply becomes zero. So you have two uncoupled equations. So this is like electron hole are independent, but they start to be codependent in case of superconductors. So electron movement is also associated with hole movement and back and forth. And this is also a feature of Dirac equation solutions, by the way. So, okay, this equation is linear, but the problem is that there is a self-consistency in the relation, which is very nasty. So UNVN Daga, and this is 1 minus 2F. Well, F is Fermi-Dirac distribution. When you plug it here, then you will see that this is essentially the Hamiltonian matrix. So the Hamiltonian matrix will depend on eigenstates and eigenvalues at the same time. So in that sense, this is very nonlinear quantum mechanics. And as you're supposed to know, the quantum mechanics theory is linear. So in that sense, this is how to say, this feature which makes it different from classical Schrödinger equation. Nevertheless, it helps a lot to know the structure of Schrödinger equation solutions because you see, if this delta is very small, which usually it is small, it's just a perturbation essentially, right? So basically solving this equation 20 is the way to describe superconductor and non-superconductor interface problem. You can also have relatively trivial case when you have uniform superconductor. In principle, equation 20 is also able to describe levitation phenomenon. By the way, you have also the equation for current density, which is very much similar as you have two contribution to current from both electrons and holes, by the way. So it's a generalization of Schrödinger equation for current density. Well, it definitely needs some detailed classes on solving some problems. I'm just now giving general remarks. All right, and now I want to switch to Ginzburg-Landau theory because dealing with that, well, you can think about the following problem. You have superconductor interface to non-superconductor interface. Superconductor has uniform delta X, and then suddenly it drops to zero. So compute me UNVN at the boundary. Basically, you're supposed to get exponential decay. Or you can describe superconductor, non-superconductor, superconductor, like this Josephson junction. So the equation 20 gives you this description of Josephson junction. And so on and so on. All right, so this was just general view. And now let me talk a little bit about functional analysis, and then we'll jump into Schrödinger, into nonlinear Schrödinger equation. That is Ginzburg-Landau. Are there any questions so far in reference to given statements? All right, so I will continue. All right, so this is, okay, the functional derivative. Well, I'm not going to replace, mathematical physicists from their positions, in the sense that they will give you more insightful and detailed definitions. I'm just giving operational definition. Operational definition of functional derivative is formula 21. So what's the difference between classical derivative and functional derivative? Well, the argument of real value function, for example, is real number. The argument of functional is another function. So just let's say, imagine that, so what is a functional? You can imagine integration from minus infinity to plus infinity g times gx times fx dx. And then you can always set g to have to be a certain function, and then f is argument. So you this integration will give you different results, but it's a formally functional. Functional is just about argument replacements. You replace the argument of being real value by set of functions. That's it. And then this is this notation which is used here. It's change of functional with respect when you consider the change of this functional argument in a sense, and there is fy and there is fx as. So usually the functional has the square brackets that constitutes the functional, and then what is the formula? So you have epsilon, which is like infinitesimal, infinity small value. So you make a push into x Dirac xy times epsilon. So this is argument, and then minus functional without this push over this epsilon. This is formal definition. And then turns out that you can Euler-Lagrange differential equations of motion can be derived from that, or Schrödinger equations of motion can be derived from that, or Ginzburg-Landau equations of motion can be derived with that concept. So there's a concept that said that the functional is minimized with respect to different physical fields, and then you get the equations of motion. That's how it is. All right. Let me move to very particular example, and then this is Schrödinger equation and Schrödinger functional. So let me introduce Schrödinger functional. Schrödinger functional is like, this is mean value of this Hamiltonian. So this is like, this is prescription for Schrödinger functional in first quantization picture. So then is just, this is psi daga. So this is like density of electrons, right? So it's a mean value of this function across the whole space. And then there's this functional, since in general case we have dependence on effective potential, and which is given, but so the solution of that of Schrödinger equation is actually the distribution of wave function and distribution of currents, or distributions of distribution of currents, or this will be later translated to, could be translated to distributions of vector potential. So you can treat C, so wave function and vector potential as arguments of this Schrödinger function arguments. And this is very interesting that this solution, so you are giving the effective potential, then you're searching for the solution. Let us, for the sake of simplicity, forget about vector potential. We just search for wave function. It turns out that the solution of Schrödinger equation minimizes this function always. So if you make a trial function that is less fitting to solution, it will have higher energy than the function that is closer or is finalizing the solution. So you can come into, so the solution of Schrödinger equation is nothing else as minimization of Schrödinger function. That's very important. And formally, you get two equations of motion, Schrödinger equation and current density. Yeah, that's supposed to be A, I'm sorry. This is current. So Schrödinger equation of motion is this one, and then the current density is this one. So you get two equations of motion. So forget about, basically you can forget about Schrödinger equation. Everything is Schrödinger function. That's this way of philosophy of this is a slight shift of paradigm way of thinking. And then if you look on physics in terms of minimizations of some effective functional, then you get very powerful methods. And one of the most powerful methods ever seen is a relaxation method and the gradient descent method. The gradient descent method is used in neural networks. So in neural networks, you also minimize some type of functional, actually. There is a beautiful paper. It's called The Universe in Neural Network. Please search for it. It's published not in MDP and Entropy, but it's by Russian physicists. So he describes the concept of learning of neural network by minimization of some functional. It's very much in terms of physics. Anyway, the Nobel Prize was given for artificial intelligence inventors. They have very much used a kind of methodology now in physics. Anyway, so this is a matter of exercises, and now we are going to transfer to simpler methodology, which is Ginzburg-Landau. But before moving it, I just want to cite some simple facts. Well, we have a missing part of this our activity is actually lack of exercises. This is very much bad feature for our detailed insight, because we have to be pushed to solve certain problems in a very detailed way. But okay, and now I will just touch a little bit issue of quantization of magnetic flux. And this is very much with storing of energy at some point. What is the easiest way to store energy on the moon, where it's quite cold? Well, it is a super usage of superconductor. Let's say you have 10 Kelvin of effective temperature, let us say. 10 is minus 263 Celsius degrees, let's say. You are in the shadow part on the part of moon that is not subjected to sunlight, so it does not heat up. Then you can use some high temperature superconductor or low temperature superconductor. You can set the current flow, and this current flow will go for infinity, actually, because there's no dissipation, essentially. Maybe not infinitely long, but very long. There are some intrinsic dissipative effects in superconductor, but in first approximations, they could be omitted. So there is, if you have flow of current, you have magnetic field, but what is a very peculiar feature is quantization of magnetic field. There is superconducting ring, there is magnetic field coming out. And due to the fact that after rotation, wave function has to come back to the same value, so the phase of wave actually has to be changed by 2pn after one rotation. So this will imply the quantization of magnetic flux. Quantization of magnetic flux, and then, so this is quantization of magnetic flux is also a very prominent feature of superconductors. And this has to be dealt. So it has to be obtained, for example, from Ginzburg-Landau theory or from Bourdieu-Dijen theory. It has to be described. All right. And then we will try to deal with that. Now I'm moving a little bit towards, I would touch thermodynamical methodology, and then you will see. I probably will focus more next time, give you a more explicit case. Now I give you some kind of conceptual projection on that topic. Free energy functional Helmholtz free energy concept will be used. And first, you have to deal with this concept of second order phase transitions. So what is difference between first order phase transitions and second order phase transitions? Does anybody of you can say to me, what's the difference, please? Yeah. What's the difference? Eric, do you know that difference? Wojtek, do you know the difference?
I don't think so.
What type of phase transitions you know? No, come on. What's the simplest phase transitions you know from elementary school? Wojtek.
So, for example, melting. In English, I check it.
First order?
Melting of what? No, come on, in winter, what we have in winter? Melting of water, of ice, right? Wojtek?
Yeah, for example.
What type of phase transitions is melting?
What do you mean by what type?
First, second, third order phase transition. What is characterized? Yeah, then why phase transition is occurring in general? Why is occurring in general, the phase transition? Eric, why phase transition is occurring? For example, if there is a ice melting, what happens with crystal structure, with density? What is it? Is it dramatic change of density when you have when you transfer from liquid water to ice? Is there a transfer?
The density changes, but with water is an exception, right?
No, but I mean what is really radically, I would say, prominent. The Yanis also has answered on the chat, but anyway, is this continuous change of density. So in a sense, it's abrupt change, right? But I would say number of symmetries occurring in water and ice are different, right? Can you see that number of symmetries occurring in water and ice are different? Like, let's say there is different, basically the ice is stiff, right? There's a feature. So stiff ice suggests that crystal lattice is ordered, right? Might suggest or has certain level of order. And since water is soft in a way, it has less ordered lattice, you can say, or disordered lattice, right? So you can sense that there are different symmetries occurring. So the phase transition is associated with let's say, change of symmetries, right? But the question is how these symmetries can they change in a dramatic or less dramatic way? So what do you think? So in a sense, in case of ice, it's very noticeable that the pipes can break, right? If you have the pipe full of water, suddenly transfers to ice. Ice has different volume, has bigger volume. It can crush, the pipes, right? So this is very sudden change. But so this transition is first order phase transition. The from ice to water. But there is, and this is there is a second order phase transitions, no, and third order phase transitions. So what is the difference of it? Okay, maybe different example. Magnetization is occurring for certain temperatures, and above certain temperatures magnetization drops, right? Is it intuitive for you to know that? Magnetization, right? Yeah, Eric,
Yeah, I think so.
Yeah.
It's intuitive.
And so let's say there's Landau functional, which describes magnetization, and there's a Curie temperature. Do you know what is a Curie temperature and Curie transition?
Yeah, then on the University of Technology is in the lab is a special experiment.
Yeah.
About the Curie temperature.
Yeah, but what is typical Curie temperature known to you? Any particular examples of Curie temperature? Okay, maybe in a different way I will ask. And then, yeah, I know that I catch you a little bit by surprise, but that's the whole point. I mean, it's to it's the if you suddenly discover something new, you know that your gap in knowledge is going to be filled with new information. But otherwise, if you don't really have this discovery of new things, then you can presume that the lecture is pointless. It doesn't give you new things. So in case of ferromagnet, for low temperatures, we have ordered magnetic domains, right? Right? Wojtek, do we have?
Yeah, yes.
And for higher temperatures, these domains can have chaotic orientation or just arbitrary orientation, right?
Yeah, that's true.
So how is that? For low temperatures, you have more symmetries, or for high temperatures, you have more symmetries? What do you think? What's your intuition tells you?
In low temperature, you don't have symmetry.
You have lower number of symmetries.
Yeah.
Yeah,
exactly.
Yes. So you see that. So you suspect that, let's say, in low temperatures you have less number of symmetries, and then when you go to higher temperatures you have more number of symmetries, and then but the ferromagnet is the case of second order phase transition, and then actually this you can diminish magnetization if you increase temperature, but you do this in continuous way, right? So it's characterized by continuous parameter. This is magnetization. So it's actually it's Landau phase transition. It's a theory of Landau phase transitions. There are the whole books on that. And then you have very much, yeah. So, and then you need to know why it's beneficial for the system to take let's say order parameter. So in a sense, magnetization is example of order parameter, right? So Landau theory of phase transition was first. It was about ferromagnets and so on. But then was Ginzburg-Landau phase transition, which used similar arguments, but the similar arguments were, let's say, but it was done with respect to this density of Cooper pairs, actually, and or just, I mean, the order parameter, right? So then there is some order parameter denoted by NS letter. And then you have this theory with, so if your order parameter lowers the energy of the system, it's favored by nature. That's it. So in a sense, you can have variational formulation of electromagnetic laws, and this is minimization of also the functional. So the equations of motion between charged particles take such structure because it minimizes the presence, the total energy. Usually it's this argument. Most parts of physics, not all, can be formulated by minimization of functionals, actually. Minimization of functionals or minimization of integral differential equation. This also always results in integral differential equations. So that's essentially the philosophy of physics. All right, and there is also, then before moving on, Helmholtz free energy. Do you know what is Helmholtz free energy? Any of you does know it or not? What is the thermodynamical potentials? Eric, what is Helmholtz free energy? It depends how you denote it. It's now denoted by G, but it's internal energy minus T times S. T is absolute temperature and S is entropy. It's a concept of thermodynamics where the work of closed system with constant temperature and volume. So we have constant temperature and this constant is measured using thermodynamical potential. So it's a form of thermodynamical potential. And we want to minimize Helmholtz free energy. And then we parameterize it by in the way as we minimize it in the way as by postulating that it is in that form as given here. So there is order parameter ns square, linear and ns square. Okay, so let's say I will later we are going to replace ns by c square. C absolute value of c square and absolute here will be c to the modulus c to the power of 4. That's what are we going to continue on the coming lecture. And let's say I will I would say then with this on the coming lectures we are going to have the emergence of non-zero order parameter that that takes place. But yeah, before coming to next lecture, let's say, I want to ask you to do a few things. So first of all, derive this equation, Schrödinger equation, with usage of functional derivative, and derive current density equation using the functional derivative with respect to the here is A field. Yeah, and then having those two, yeah. So this is somehow necessary to feel things deeper, right? All right. So let's say, I believe that since we already took quite long time this lecture, I suggest that we can stop now, and I also can take questions. So it's desirable to attack the Ginzburg-Landau problem in great detail on coming week. And also, I also try to point out the existing numerical methods. So usually there is a philosophy that, okay, so from formal perspective, the Landau-Furey phase transitions is only valid for temperatures close to Tc. Tc is when this order parameter is dropping, right? So like magnetic ferromagnets stop to have orientation. This is this critical temperature, right? So yeah, and then we need to attack this Ginzburg-Landau problem in deeper way. Eric, do you have any questions in regards to giving a lecture? There's no questions. Radosław, any questions, suggestions? Yanis, any questions or suggestions? All right, I guess that's it. Wojciech,
Good discussion.
All right, thanks. So I suggest to finish.
No, I don't think so.
Wojciech, anything else to add? Wojciech?
No, I don't think so.
All right, thanks. All right, guys. So I suggest we continue next week in the same mode as we are doing so far. And thanks for your presence, and I welcome you next week. Thank you.